Good morning, everyone. So we are working on the gas laws chapter. A couple things to note. I mean, we are coming into the last 3 or so active weeks of class, and then we've got finals week. So just make sure you are staying on top of stuff. If you've had an assignment or two that's been missed in there, try not to miss any more. Let's just push through and get everybody passed. As far you guys are doing pretty well. I've been impressed. Especially I know with this online format, it can be tough. So just hold out a little bit longer. I do believe course evaluations are out. So you can evaluate the course. You can evaluate me, you can evaluate online format. They're totally anonymous, so they are helpful. You can let me know what I'm doing well. Let me know where you see room for improvement. Also, if you haven't gotten with your advisor yet to sign up for summer and fall classes, make sure to do so. Enrollment, I think, was slightly down. They're not seeing quite as many people enrolling early for classes. So the sooner we can get you all enrolled in classes, the more options really that are going to be available for you, because otherwise they'll start dropping sections and then it'll get really narrowed down. So go ahead and sign up. As far as summer, I'm only teaching an online 092 class. But if y'all are planning on coming back in fall, and I believe that they're going to be, they're planning to be in person, and I want to teach in person. So if you're interested in that and you want to take another chem class with me, I do teach Chem 130 if you're going more into like a vet tech medical degree. And I also teach 151 if you just need Gen Chem 1. So I would love to have all of you in another chemistry class with me. I have quite a few people who end up going from 092 and taking higher chemistries with me. And it's always nice to see familiar faces. So come back around. Let us gas law. So last time we were talking about all these different laws, and we had everything that we've talked about thus far has been equations that you would use when there's some sort of change in the parameters. So the pressure is changing, how does it affect the volume? The temperature is changing, how does it affect the pressure? Things like that. So here are the equations. The ones represent our initial parameters, the twos represent our finals. Which one you use is really going to be based off of what variables the equations are talking about, right? I want to write out sort of a general equation that you can kind of derive all of these from. So I guess that's in my 092. That is chemistry, actually. I know it looks like my daughter did a drawing there, but that is chem. If you come take organics, you will get to learn all that stuff. Okay, so I'm going to smush all the equations that we have together into one big massive equation, and it's going to be P1 V1 over T1 N1 is equal to P2 V2 over T2 N2. So if you have this written down somewhere, you can really derive all the other equations. Like let's say the equation or the problem that you're looking at says temperature is constant and amount is constant. Well, then we don't have to bring those into the equation. What are you left with? Boyle's law. So there's Boyle's law. Okay, what if instead it says that pressure stays constant, like you're staying at sea level, and amount of gas stays constant? What are you left with? V1 over T1 equals V2 over T2. That's Charles' law. So this is kind of a nifty way to have all those things smushed together, all right? If we go back to our slides here, each one of these is hidden or is built into here. If something is going to be a constant, we can just ignore it. So I'm going to give you an equation or I'm going to give you a problem, and I'll put this up here. I want you to solve for it. So let's say a 2.5 liter sample of gas at a temp of 44 degrees C is cooled to 0 degrees C. What is the final volume? So figure out which equation is suitable for this problem, and then go ahead and plug and chug. If I can move this, there we go. I'm going to just nestle this right underneath the master equation so that you kind of figure out what is the problem asking, what is it not asking about, ignore the stuff you don't need, work with the stuff you do need. I will give you all about 4 minutes to play around with that. No, 3 minutes. 3 minutes. Okay, so for this problem, a 2.5 liter sample of gas at a temperature of 44 degrees Celsius is cooled to 0 degrees Celsius. What is the final volume? So thinking about what are the things it's asking us about or talking about. So it is talking about volume and it's talking about temperature. I don't see anywhere anything with pressure or amount, right? So pressure and amount are gone. We're just dealing with volume and temperature. So the equation that we're going to want to use is Charles' law. Let me erase that so we can have. So we like V1 over T1 equals V2 over T2 for this equation. We specifically want to know about the final volume. So V2 is our variable in question. So I need to get T2 over to the other side. So I'm just going to multiply both sides by a T2. It's a divisor here. So I'm going to multiply, do the opposite, and it cancels. So we now have a new equation. Well, not a new equation, but a rearranged equation that isolates the V2. V2 will equal V1 over T1 times our T2. Now we need to put all of the information from the problem into the appropriate variables. So my V1 is going to be my initial volume. That's 2.5 liters. My T1 is my initial temperature. So my initial temperature is 44 degrees C. Now remember, Celsius cannot go into this equation. Why can volume be, in liters or milliliters, but temperature has to be in Kelvin? Because in order to convert from liters to milliliters, we use a multiplying factor in dimensional analysis, which would have the same effect on both sides, right? So if I'm going from liters to milliliters, I would multiply one side by 1,000 and the other side by 1,000. That would have the same effect because it's a multiply divisor. But in temperature, we have to add 273. If I add 273, that's a different order of operation level than multiplication division, which is how this problem is set up. It will throw the whole problem off. So we need to make sure we do this before we insert it into the problem. So T1 is going to be 44 plus the 273, and we get 317 Kelvin. Our T2, or our final temperature, it's originally 0 degrees Celsius. That's what it's given. We're going to add the 273 for 273 Kelvin. So just conceptually, what are we doing to the temperature? We're lowering the temperature. Well, anytime we cool a gas, we would expect the volume to go down. The gas is going to kind of shrink up on us. Think of that balloon, air balloon that they put into freezing water. It'll kind of shrivel up. So the last thing is really just to plug it into the equation. We've got V2, it equals my V1, which is the 2.5 liters. I'm going to use all my units. My T2, so it is the second temperature that goes on top, the 273 Kelvin, over the T1, which is the 317. And we'll see that the units of Kelvins will cancel and we'll be left with just units of liters, which is a great unit to have for volume. And I get 2.15. And so we can really only have 2 sig figs here. So I'm going to go with 2.2 liters. Okay, so the new gases volume is 2.2 liters. Yeah, any questions on that? On why this was the equation that I used? On how it was solved? No one's got their camera on today, which is totally fine. I get it, but I can't see anyone's face expression reaction-wise. So if you do have a question, you gotta verbally say it. Otherwise, I'm just gonna go with you get it. Let me give you one more of these before we move to Pivner. So, what do I want to do for y'all? So 3.2 moles of gas takes up 1,500 milliliters. How many milliliters would 9.4 moles of gas occupy? And then general equation for us. P1, V1, T1, N1 is equal to P1, P2, V2, T2, N2. Go ahead and solve for that. Sorry, my younger kid was like screaming bloody murder there. Okay, she's quiet now. Someone is watching her. Okay, so go ahead and figure out what you want to solve for, what you can kind of ignore. And I'm just gonna give you 2 minutes for this one, quick one. Okay, so this problem is using Avogadro's law, but again, like I'm not a stickler about you knowing that it's Avogadro's law. What I want you to do is be able to look at the problem and say, okay, what is it asking about and what can I sort of ignore? So does it talk about, it talks about amount and it talks about volume. We don't talk about pressure, so let's ditch pressure, and we don't talk about temperature, so let's get rid of temperature as well. So we're looking at V1 over N1 equals V2 over N2. Remember the N is talking about moles and it needs to be in moles. Are we in moles? We are in moles. So we just want to figure out what everything is. So V1 is a volume, 1500 milliliters. For these initial finals, volume can be in milliliters or liters or whatever it happens to be. It's just important that they're the same on both sides. N1 is the initial mole value, so 3.2 moles. We don't know our final volume. That's what we're trying to solve, and it wants it in milliliters, which is good because we're given milliliters. And our final amount of gas is 9.4 moles. So we're just going to plug this into our equation. What did we say we were going to solve for the final volume? So we need to move N2 to the other side. So we're going to multiply this by N2. This is our equation here. N2 times V1 over N1 equals V2. So V2, let's start plugging and chugging. Our V1 is 1,500 milliliters. Our N2 is the 9.4 moles all over our N1, which is our initial 3.2 moles. And so if you see what's happening here, we're taking our volume, because it's a direct relationship, as one goes up, the other goes up. We're taking our volume and we're multiplying it by however many times the moles have gone up, right? It's 9.4 on top, it's 3.2 on the bottom. So we've roughly increased it by like a factor of 3, maybe a little more. So we're taking that increased factor and we're just multiplying it by our volume because it's a direct relationship. Moles will cancel and we'll be left with milliliters. So my volume should be bigger. If it's not, we've done something wrong. We're going to take the 1,500, multiply it by the 1,500. Oh my goodness. Come on, calculator. 1,500 times the 9.4 divided by that 3.2. And I've got a big number, 4,400 milliliters, which makes sense because this is an increase of roughly 3, right? Our volume should also increase by roughly 3. It's close enough. Okay. Great. So let's go to Pivnert. We've already talked. Where are you? PV equals nRT. Okay. So we can take all of these things and actually combine them into a law that's called the ideal gas law. Again, all these things only apply to gases. But in the ideal gas law, there's no initial and final. We are sort of frozen in time with very specific parameters for that given time. And the ideal gas law states that there is a relationship where the pressure times the volume of a gas will always equal the amount of gas in moles times this thing called R, which is an R constant, times temperature. All right, that's always the case. So in this equation, you are given, you have 4 variables, 1, 2, 3, 4. R is a constant, all right? This is the R constant. It's 0.0821. The units are really funky on it. Liters times ATMs divided by moles times Kelvin. Yes, it has 4 units in it. So this is a situation where I could say, hey, a gas has this pressure, this volume, and this temperature. What is the amount of gas? And you could solve for that. Notice there is no initial or final. We're not changing anything. So I'm not saying, hey, my initial pressure is this, and my initial volume is this. We're not doing any of that initial final. This is frozen in time. Why does R have these funky units? Well, let's isolate for R just because I like to do that. Whenever I can sort of try and explain why something is the way it is, I like to do it. So we have Pivnert is PV equals nRT. When I say Pivnert, I'm just sort of trying to sound it out. So if I isolate for R here, that means I'm going to move temperature and amount to the other side. So R equals PV over NT. PV over NT. Well, what are the units of R and what is R? It's 0.0821 ATM times liter over mole Kelvin. Pressure ATM. Volume, liter, mole is N, and T is the Kelvin. That's why it has those funky units, because R is equal to these. Gases do this really amazing thing that these values, when you take these two and multiply them and divide by these two, you will always end up with this number, always. It's just how it is. Now, remember when I said in the previous problems that pressure and volume could sort of be in whatever units as long as they were the same on both sides? That is not the case when you're using PivNert. Because PivNert has a constant that has these units, your values have to be in those units, okay? So pressure has to be in ATM, volume has to be in liter, amount, moles, temperature, and Kelvin. Those we've already sort of consistently said. So going back to the slides here, it says that, explicitly, pressure, make sure it's in atmospheres, volume, make sure it's in liters, amount in moles, temperature, and Kelvin. R is not always written in the problem. So if you're given a problem and you have to use PivNert and you're like, I only have 4 or 3 of the 5 things, don't I need 4 of the 5 things? It's because R, you need to remember, is this constant. So let's try one of these. Here we go. It says, calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 ATMs and a temperature of 315 Kelvin. So outside of the fact that it tells you right at the very top to use the ideal gas law, what are some indicators that you would want to use the ideal gas law here? You're given 3 pieces of information. There is nowhere where it talks about change in parameters. So we're not given an initial set of variables and a change into a final set. We're frozen in time. When you're frozen in time like that, you're going to want to use PivNert. So I'm just going to write PivNert up here for you. PV equals nRT. I trust that you guys can work with equations at this point, so I'm going to have you go ahead and solve for it. You want to find volume. I'll give you all about 3 minutes to work through that, since you don't really have to do a whole lot of. Okay, so we're going to use PivNert here. And we want to solve for volume. So it's asking about volume, and it gives us this information about other things. So we have the amount of gas in moles, we have the pressure in ATM, and we have the temperature already given to us in Kelvin. So this one is actually pretty easy because you don't have to convert any one of these. That isn't always the case. It could give you the amount in grams and you got to convert to moles. It could give you the pressure in mmHgs and you have to go to ATMs, right? And this could be in Celsius and you have to go to Kelvin. So we want to go for volume. We need to take our PivNert and isolate it in such a way that volume is by itself, which is pretty easy. We're just going to move P to the other side. It'll be below the fraction bar. So we've got V equals nRT divided by P. Now, I definitely like to plug my units in here, all right, because it confirms as things cancel out. So we have our mole, which is our N value. We have our R with our funky units. We have our temperature, and then we put the pressure below. The moles will cancel, the ATMs will cancel, and the Kelvins will cancel, and we'll be left with just liters. What we end up with is 16.0 liters. So it's just a plug and chug. Questions on this, we will do another one, but questions on using PivNert or identifying when you use PivNert versus Charles or, Boyles or any of those. All right, I'm gonna give you guys another one separately. So let's go with, 55 grams of O, and that's a little subscript too, okay? It's O2, it's the diatomic. So 55 grams of O2 temp of 33 degrees C and a Okay, 55 grams of O2 at a temperature of 33 degrees Celsius takes up a volume of 528 milliliters. What is the pressure of this gas? So this one's going to take you a little bit longer because you got to match units. So I'm going to give you guys 5 minutes for this one. It is a PivNert problem. We don't see any sort of change in amount or volume or anything like that. Just another 30 seconds or so to kind of finish up your train of thought. Okay. So here we've got a problem where we're going to be using PV equals nRT. We want to solve for pressure, so let's just get pressure by itself. Pressure should equal N times R times T over volume. So we know that R, which is a constant, is 0.0821, and that's ATM times liter over mole times Kelvin. Sometimes it's nice to just write that one first, because then as you put the other things, variables in, you can see, oh, I got to match those units. So what is our, we've got the amount of gas, which is N, which is 55 grams of O2. I need it to be in moles. So I've got to get out of grams into moles. 1 mole of O2 weighs 32 grams of O2. Remember, this is a diatomic. Anytime you see it stuck to itself, you got to add 2 of them together. If you didn't have to add 2 of them together, it would just say O, but it says O2. So make sure you're doubling it up. So we take our 55 and divide it by 32, and we get approximately 1.719. I'm just gonna, with that many moles of O2. All right, next thing we have, we know the temperature. So temperature is 33 degrees Celsius. Well, I have to be in Kelvin, so I'm gonna add the 273 to it. So 33 plus the 273 gives me 306 Kelvin. The last thing I have is volume. I know the volume is 528 milliliters. And for Pivnert problems, I need to be in liters. Okay, so I'm going to convert that from milliliters to liters. However you want to do it, I'm just going to hop the decimal over. 1, 2, 3. That is 0.528 liters. Now I'm in moles, Kelvin, and liter. I can then put it into the equation. All right, these values over here will not work. It has to be these. You'll just get the wrong answer. So pressure should equal the amount in moles, 1.719 moles of O2, times my R value, 0.0821. And again, I'm going to put it in as ATM, liter, mole, Kelvin, times temperature, so 306 Kelvin. This whole thing, we're going to divide by the volume, which we said was 0.528 liters. Let's see if the things cancel. Mole with mole. Kelvin above, Kelvin below, liter above, liter below. So we're left with just units of ATM, which is a great unit for our pressure. Plug it in, 1.719 times the 0.0821 times the 306 divided by that 0.528. And I get like an astronomically high pressure. Not astronomically, but high. 81 point, I mean, what are my sig figs? It looks like I'm going to go with 2 sig figs. So 82 ATMs. Is that what y'all got? Carrie, I can see your face, so I'm going to ask you. Is that what you got? Awesome. Cool. Okay. 82 ATMs. 82 times the pressure that we would experience at sea level. So hopefully this doesn't feel like too challenging. If you're, I mean, it's just plug and chug. That's all we're doing really is plug and chug. The hardest, not the hardest thing, but the sort of the trickiest thing is just making sure that the units are matching. Okay. What will happen is we just kind of get in a groove. We're on a test. We're like, oh yeah, I'm just going to bam, 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 plug this into PV equals nRT. will make sure you're honoring the units that Pivner needs. Okay, couple things to note. Like conceptually, gases do not always act ideally. So these really convenient equations that feel just so neat and precise and like almost too neat for reality's sake, well, they don't always apply. There are non-ideal gas conditions, specifically if you're at a very low temperature. So if the gas is really, really cold, or if you're at a high pressure. Any environment that's going to cause the gas to come closer together, right? Because normally gases are made up of a lot of space. So these particles are acting independently. Because the particles are acting independently, those rules apply. Once the particles start to kind of stick together or like attract or repel each other, that's when the rules start to fall apart, right? So low temperature, it gets really cold. They come closer together. They're going to interact. High pressure, you push down on the gas, you bring this gas really close together, it's going to interact with each other. Those equations aren't going to play. But again, we are talking mostly about this situation, these ideal gas conditions, which is high temperature, low pressure. So there's this rule of partial pressures, or the mixing of gases. So according to the kinetic molecular theory, all the gases in a container are acting independently. So if I've got oxygen and nitrogen and argon, they're all going to do their own thing. They don't even like know the other ones are there. So because of this, the pressure due to any individual gas in a mixture is known as its partial pressure, and it's totally isolated from the other ones. So like if I have a room full of nitrogen, what do they have as an example? They're using the atmosphere. So we've got nitrogen, oxygen, and argon, and a little bit of carbon dioxide. The nitrogen has a certain partial pressure, and it makes up about 78% of that partial pressure. Oxygen is 21%, argon is 0.9%, and carbon dioxide is 0.04. So each of them is giving their own pressure. And when you add them up, you get the total pressure. So total pressure is going to equal each of the partial pressures times whatever percentage they are. So in this case, if I've got a total pressure of 1 atm, and helium makes up 80% of it, and neon makes up 20% of it, in order to get the helium's partial pressure, you take the total and you just multiply it by whatever its fraction is. So it's 80%, you take the 1 times 0.8 and you get 0.8, right? The neon is the remaining 20%. You take the total, you multiply it by the 0.2, and you get 0.2. So these two things added together equal the total pressure. It's very simple. This is Dalton's law of partial pressure. I don't even think I actually have you guys do anything with the percentages. I just keep it as simple as this. So you've got your total pressure. It will equal all the individual partial pressures added together. How many partial pressures are there? It depends on the mixture. So for air, usually we say there's roughly 3 gases. There are trace gases as well, methane and CO2, but the biggest ones are going to be nitrogen, oxygen, and argon. When I add those together at sea level, they should equal 1 atm. So let's try a problem with this. It is really this simple. Just make sure the units are the same too, okay? So a mixture of helium, neon, and argon has a total pressure. So let's even just write that out right now. P total pressure of 558 mmHgs. If the partial pressure of helium, so the pressure of helium is 341 mmHgs, and the partial pressure of neon is 112 mmHgs. What is the partial pressure of argon? Well, it is an addition subtraction problem. So P total always equals the individual things added up. So P total for this one should be equal to P helium plus P neon plus P argon. You know the total, you know helium, and you know neon. So how do you solve for argon? You just take the total and you subtract these two values. That's all you do. Whatever remains is the pressure that we're experiencing from argon. So we take our 558, let's strip away 341 from the helium and then strip away 112 from the, what is that, from the mercury. Sorry, I don't know, neon. Oh yeah, sorry, neon. And we should get 105 mmHgs. Partial pressures should always add up to equal the total pressure. It's gonna be that basic for your test. Think you can handle that? You guys got that, yeah. You may be given the individuals and you have to find the total. You may be given the total and some of the individuals and find the other one, but that's really the extent of it. Okay, we're in toxicity, great, yeah. I'm not gonna go over this. We aren't doing anything with vapor pressure, so I won't have you collecting gas over water. We're not doing anything with gases and chemical reactions. Just conceptually what's going on here, because you may see it on a homework. Using PivNert, you can solve for N, which is the moles. Anytime you can solve for moles of one thing, you can use the coefficients in a balanced equation to find moles of another thing. So that's the extent of that. This I do want to talk about though, okay? STP, so standard temperature and pressure. So when you are at standard temperature and pressure, and that is, temperature is 0 degrees Celsius and pressure is 1 atm. The problem will say, hey, you're at STP. You can use this nifty conversion factor. It only works at standard temperature and pressure, but it says that 1 mole of any gas, doesn't matter what it is, will occupy 22.4 liters. How cool is that? Real quickly, you can go from moles to liters or liters to moles. Only works with STP, but does apply to all gases. So if we look at this next slide here, both of these gases are at standard temperature and pressure. On the left, we have helium. On the right, we have xenon. They're different gases, but because they're both at STP, 1 mole of each of these will occupy 22.4 liters. Cool. So let's do a problem with this. How many liters does 84.6 moles of CO2 take up at STP? How many liters does 84.6 moles of CO2 take up at STP? I'll give you 2 minutes for that. Okay, so for this one, you know, if you see STP, you might just want to make a note. Okay, 1 mole of whatever I'm dealing with, 22 point, what's going on there? 22.4 liters. You can kind of just write that out. This is a conversion factor and it applies to any gas. So we're dealing with CO2. This will work just fine as long as it's a gas. So 84.6 moles of CO2, that's our given. And we know that for every 1 mole of CO2, 22.4 liters is what we should get. So moles will cancel and we'll be left with units of liters. We literally are just going to take the two values and multiply them together. 6 times 22.4, and we get 3 sig figs here. So 1900 liters. How often are you given things in mole as in real life situations? Not very often. So let's do a problem where you're given a gram instead of a mole. All right, and you just have to do one more step. So we'll say 14.5 grams of H2O gas occupies what volume at STP? Okay, 14.5 grams of H2O gas occupies what volume at STP? So slightly different from the problem before in that you're given grams as opposed to it in moles for you already. I'll give you 2 minutes for that. Okay, so this problem has us just go one step farther. If we want to do like a flow chart, we want to go from grams of H2 grams of H2O into moles of H2O. And then for moles of H2O, we can get into liters of H2O because we're at STP. So we get to use that nifty conversion. So I have 14.5 grams of H2O. I got to get it into moles if I want to be able to use that conversion. So 1 mole of H2O weighs roughly 18 grams of H2O. Right, 2 hydrogens and an oxygen. Then, because we're at standard temperature and pressure, 1 mole of any gas, in this case we're dealing with water vapor, should equal 22.4 liters of that gas. The grams will cancel and the moles will cancel. This problem up here, this started us at this step. Here we just had to do an extra step. 14.5 divided by the 18, and then we're going to multiply it by that 22.4. We get I got 18, 3 sig figs, 18.0 liters of H2O at STP. Don't use STP if you're not at STP, okay? If you're not at standard temperature and pressure, if you're at like a temperature of 350 Kelvin and a pressure something greater than 1 atm or less than 1 atm, you can't use this. You have to use PIVNERT. You would just have to plug it into PV equals nRT. This is kind of a shortcut. If you forget this, but you know what STP is, right, which is a temperature of 273 Kelvin and a pressure of 1 atm, if you plug this into PIVNERT, it'll give you the same answer as well. All right, it's just kind of a shortcut, so you don't have to use the full equation. And that is it for this chapter. Okay. I recommend, if you want to get some more practice with all this stuff, let me pull up. Ugh. Moodle always logs me out. I just want them to let me stay logged in forever. I never do. So I just want to show you the worksheet that I find to be helpful, but some of it you don't need. So before I have you use it, I want you to know that there are things on it you don't need. That one is a fine worksheet. There's nothing wrong with it, but ugh, logged out, sorry. It's the second worksheet. And one reason that I like this worksheet that I'm about to open is it has all the formulas on the front page. So everything's sort of like consolidated into one place for you. So it will give you all the information, pretty much 95% of what we have in the chapter, all in one spot. Okay, here we go. So it's a pretty big packet. It gives you Boyle's law, Charles' law, Guy's-Lussac that we don't really use, the combined gas law, Dalton's law of partial pressure is the ideal gas law. This one you can skip, okay? So Graham's law, which is the rate of effusion. This is like when you have a gas and you're passing it through a hole into another space with like a lower pressure, what the rate is, you don't need to worry about this. So leave that. But it also then has like the different abbreviations, some of the standard conversions. So, you know, normally in a traditional classroom setting, you wouldn't be able to have access to this, but while you're taking your test, I would just have this front page out. It's got like everything you could need. And then there's a bunch of example problems on conversions. It doesn't tell you which equation to use, so it's a good way to practice your skills. Obviously, if there's any problem that's talking about velocity or rate of diffusion or effusion, don't do those problems. You don't need those. But, you know, a sample of gas has a volume of 215 centimeters cubed at 23.5 degrees Celsius and 84.6 kilopascals. What volume will the gas occupy at STP? So, you know, that's a good one to use the STP equation. all jumbled together. So it's nice practice. And then it does give you all the answers at the end, right? So I recommend that for studying. So I just wanted to show you that, highlight that. Remember that the class evaluations are opening up today. So if you can evaluate, that would be awesome. Let me know what you like, what maybe you'd like to see more of. And then sign up for classes if you haven't. I'm not sure if, I know summer's up. I'm only teaching 092 over summer, but fall I will definitely be teaching a 151 and a Chem 130. So I'd love to see you all again. So we're at Wednesday, so have a good weekend. If you have any general questions, ask personal questions, hold out for a minute, and I will see you next week. Thanks, everybody.